last week, when I did that exercise where we got in a row and did the steps, that was kind of a little premature because really that would have done better today. But because at this point now, once we go through today's lecture, we'll have some of those missing pieces. So I know some of you might, that's why I sent out that email about the quiz, because I thought, oh, some of you are going to be like in a panic. Like, what's going to be on the quiz? There's so much material and we didn't talk about all the pieces. So today we'll kind of fill in the rest of the pieces. So it's again, another kind of heavy lecture, very conceptualizing, having to think of this little space, this little vacuum tube and what's happening. And not only that, we're going to exit the tube and we're going to talk about what's happening, not super in depth because the next lecture is more about biological changes, but we're going to start to talk about what happens when the radiation hits tissue, cheeks, whatever, it bounces around the room. So we're going to kind of go more in depth, finish up the conversation of the X-ray machine, and then kind of add to it. So it's a bit. So I'm going to try and I have 38 slides here, but I want to try and move through it not too fast because I want you to be able to understand what we're talking about in each slide here. So, and feel free to ask questions and I can repeat myself. I don't mind doing that. So why am I advancing here but not on the screen? Okay, this is driving me crazy. Okay. Okay, so a review from last Thursday. So what are the characteristics of X-rays? It was at the very end of the PowerPoint. Does anybody remember Samtala? They travel in a straight line. Speed of light. Speed of light, that's right. Anyone remember anything else from it? They have no mass. No charge. They have mass, but no charge. Oh my gosh, now I'm going to be able, now I'm all messing myself up. No charge, but yes. So, well, now I've confused myself because you threw me off, Jenny. You asked like a really smart question that I was like, I remember some of it, but I don't remember that part. Well, particulate radiation is one and electromagnetic is the other. And now I'm having brain. Now I'm having a no mass, but no charge. Someone look it up real quick. And yes, on page 12, no mass and no mass and no charge. And particulate is mass and usually charge. Although they're in the textbook, it does say like this one thing has no charge. But generally speaking, thank you, Sahela, we'll divide it as particulate, mass, and charge, and electromagnetic, no mass, no charge. Whew, that like threw me off there. Okay, so, but what we do think about with the characteristics of X-ray radiation is visible light, they dissipate. So we think of like a flashlight, they dissipate as they come out of the source. So they move in a straight line, but they sort of like go into like this fan shape and all the individual X-ray photons sort of spread out. So they spread out or they dissipate as they leave the source. They penetrate matter differently. So depending on if they're coming in contact with something that's like low density, or thinner, they'll penetrate or be absorbed differently. They'll go through or they'll be completely absorbed by it. So, and then that shows up differently on the actual X-ray. Let's see if I'm missing anything. They're ionizing. Electromagnetic radiation is ionizing. And they do create biologic changes. So it affects the cells on a cellular level. And we'll talk more about that specifically next week. So what conditions are necessary for X-ray production? Does anyone remember those four main things? Yeah, Tala first. Yeah, we need to generate electrons. Yeah, so we need them to move quickly and then either slow down or stop. Focusing on electrons. And then we want to focus them. So we want to focus them in the general area and then make them come to a complete stop. Okay, what was the other question? What happens when I turn? So when I go and I flip on the switch on the wall and I turn on the machine, what starts happening? What becomes available? Electricity starts to flow into the machine. And then what does the electricity do? It heats the filament, and then we start to get the electron cloud, right? So one of the questions on the quiz was, it said photon cloud. It was like a little tricky because there is no photon cloud. So it's an electron cloud. So we turn on the switch and we create an electron cloud. So what happens when you hit the button? So then you have everything set up, you come out of the room and you hit the button. What did you just do when you pushed the button? They're like released from the electron cloud and they fly over and hit the anode. And then you create X-ray photons. So from there you hit the button and you kind of get that couple seconds of release of X-ray photons. And then when you stop pushing the button, it stops happening. So we'll talk a little bit more in detail about that. The questions for today. So the questions that you'll hopefully be able to answer by the time we get done with today is how are the electric currents produced? That sounds like a funny question. How are the electric currents produced? So that's one of them. We'll know how that electricity gets to where we need it to be. Where does the heat go? You guys already kind of know that, where the heat goes, because we talked about the copper stem. How do the X-rays interact with human tissue? So we'll start to talk about that a little bit too, go into more in depth with the biologic effects, but we'll start to talk about what the actual X-ray photons do when they come in contact with matter. These are the objectives for today. I won't read through them all, but this is like the area where if you can go through and broadly put in information under the objectives, that usually is a really good study tool for preparing for a quiz or an exam. Okay, so here's just a refresher picture of the X-ray tube. Remember, it's a vacuum seal. This is where I got all turned around last week when at first I said it was filled with oil, but it's not. That's the bigger tube head that's around this little vacuum sealed tube. This is just filled with nothing because they've sucked out all the air. It's a vacuum sealed tube. And it's a glass tube. And you can see here how it's kind of darker. It's all kind of dark right through here. And that's because it's leaded glass. So this whole area of the vacuum X-ray tube is leaded glass to prevent the X-rays from just bouncing out all over the place. It focuses them out. And you can see it's pretty small, like just the size of a pen. So it's not very big. And the distance between the anode and the cathode, or the cathode and the anode, is really short, like an inch or something. So do you remember which side is positive and which side is negative? Negative cathode, positive anode. Good. Okay, so let's see. Some of these are questions, some of these are just notes for myself. Okay, I'm going to move on to the next one. All right, so here's a refresher of the whole system again. So here we have, which is actually not to scale because we know that this vacuum glass tube is actually much smaller, because you've all now seen the X-ray tube in the room. It's like this big. And then we know that the tube is only like this big, so it's not quite to scale. But you have the vacuum sealed glass leaded tube on the very inside with the anode and the cathode. And then you have the larger tube head that is metal encasing filled with insulating oil all around it. And then we have these other parts that we'll talk more about today that filter out different weaker X-ray wavelengths, and then they come straight through this BID. Here it's called the positioning indicating. I think I have to just commit. I hear myself say PID and BID, and I'm like, Leslie, pick one. But they're the same, and it kind of sounds the same coming out of my mouth, like P and B sound very close. So I don't know which one I prefer yet. I feel like I toggle between the two of them. Some of my notes I have BID, but one is just positioning, and then the other one is beam indicating, and the other one and one is positioning. It's the exact same part. It's the long piece, the cone that's coming out of the tube, or the big tube head. So these are all, this is sort of similar to that exercise we did where we filled in the different parts. So that's sort of the answer sheet for that. So here's a definition of electrical current. So electrical current, it's the flow of electrons through a wire or a circuit. So electrons are flowing, and I am no electrician. My knowledge is going to cap off pretty quickly here, but when we have an electrical current, we have electrons flowing through a wire or a circuit. And we know that we get that from our outlets in the wall, right? And typically in America, it's a standard 110, 220 if it's a bigger, like a bigger piece of, kitchen or appliance or something like that, but typically 110, and they all look the same. In other countries, they do look different, and they're not they're not interchangeable. But in the US, we have our standard wall outlet that's usually 210, 110 or 210 or 220. Our currents from a typical wall outlet is called an alternating current, meaning that the current flows in both directions, in alternating waves. So it goes one way from negative to positive, and then it goes from positive to negative, and it alternates. DC is direct current, meaning it only flows in one direction. This, I think that this could possibly be a typo. I mean, I think this is an image that was cut and paste. I'm not sure why it says AB. I feel like it should say AC here and DC. I looked at that earlier and I was like, whoa, wait a minute, why does that say AB? Does anybody have an idea? I feel like it's like an incorrect image. So I might have to do a little editing on this film. AC, alternating current, DC, direct current. And you'll see how that comes into play in generation of radiation here in just a minute. So X-rays are only produced in one direction. And we know that because we know where the electron cloud happens, right? We know it happens over on the negative side, and then they fly over to the positive. So X-rays are only going to be produced during that cycle when the electricity is flowing in. They're only going to happen when it's in the negative to positive cycle of the electricity flow. Because since it is alternating current, negative to positive, positive to negative, there's going to be a time when X-rays are not going to be produced. Does that make sense? So it goes along with the fact that there's only a specific time that X-rays are possible to be produced, because there's only that window of when they go from the negative cathode to the positive anode. So you can see here, it happens in pulses. So X-rays are produced, then it goes into the other current, the opposite current flow, and then it goes back from negative to positive, and then it goes from positive to negative, so no X-rays are being produced. So that's what's being shown here, is this, we're only getting X-rays during that specific cycle. And the cycle happens very fast, like super fast. 60 pulses happen in 1 second. So it's very, 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 very fast. So it almost seems like, it's a constant stream of X-rays, but it's just pulsating incredibly fast in 60 times in 1 second. So we have 2 circuits for X-ray production. And I don't know if anybody watched those videos that were embedded in the PowerPoint, but I think the one where the guy was holding the actual vacuum tube and he was talking a lot, I think he kept pointing to or talking about the step up and step down. And I know it was mentioned in the other video too. And so that might've been like, what was he talking about? I don't even know. Because we hadn't gotten there yet. So it talks about the two step up and step down transformers. So a transformer is something that can either increase or decrease voltage. So it can either make more voltage or make less voltage. So we have two very specific transformers in the tube head. Well, it's not in the tube head, it's actually over on the wall. It's in that part that's mounted up on the wall. And those circuits are there to reduce the amount of voltage that's coming out of the wall. And then the next one is meant to boost it up to get those electrons to fly over to the anode. So the filament circuit takes 110 volts of electricity from the wall and it reduces it down to 3 to 5 volts because the filament, the tungsten filament, couldn't handle that direct 110 volts. It doesn't need that much to create the electron cloud. It would just overload it. I don't know what it would do. Maybe it would break, maybe it would explode. I have no clue, but it can't handle it. So it has the step down transformer to reduce that voltage to 3 to 5 volts. And that is controlled by the milliamperage. It's really important that you know that that side of it is controlled by MA. Next, we need to have the voltage increase now. So we've reduced it down, we have an electron cloud, but now we need more energy to boost this process to get the electrons to go over to the anode. So now we have a step up transformer, and it's going to take those voltage and it's going to ramp them way up to 65 to 100 kilovolts. So it really intensifies it. And that happens on the step up transformer when you push the button. So it only happens sporadically when you push the button. You get the step up transformer comes into play, adds more power, more volts, and then the electrons are able to fly over to the anode. The auto transformer, I don't know if this is on my next slide, but it says auto there, so I'll just say it. The auto transformer is there to sort of keep everybody happy, keep the machine from short circuiting, keep the lights from flickering when you push the button and you get this surge of electricity. It's there to just kind of regulate everything. And that's why it's called auto transformer. It just kind of regulates everything and keeps from affecting other things around it, like the machine short circuiting or the lights flickering, stuff like that. So some specific things about the transformers and why they increase and decrease voltage is really, really important for you to know here. So the step down transformer, we know it heats the tungsten filament and we know it's controlled by MA. So those are some important points. But why does it decrease? What makes it specifically decrease the volts? So what happens is on these transformers, you have two sets of coils, just wire. I just imagine it as just like the picture, wire wrapped around a piece of metal. And you have two coils, a primary coil and a secondary coil. And I kind of think of it as the more coils, the more potential for energy. In my head, that's just how it works. There's more coils, more energy. I don't know if that's even true, but that's how it made sense in my mind. So if the primary coil has fewer turns, fewer times where the coil is wrapped around it, fewer turns, and then it goes to the next secondary coil and there's a lot more, then you're stepping up. That's stepping up the energy and it's going to increase in voltage. If you have more coils on your primary than on your second, you're stepping down and you're going to reduce the energy. So you always come to the primary coil first, and whether or not the secondary coil has more turns or less turns indicates whether or not the voltage goes up or goes down. Questions on that? You just have to paint a mental picture, I feel like. Yeah. So if you're like a little electron and you're traveling through the circuit and you come to the transformer and let's say there's 5 coils and that's your primary circuit. And then you go to your primary coil and then you go to the second one and there's 10, it's increased. And so there's more potential for energy and that's a step up. Now, if you come to it and there's travel down the circuit line and there's 20 turns in the primary coil, and then you go to the secondary one and there's 5, that's a step down. You're going to reduce your energy, and that's a step down transformer. Paula? Not the tungsten. So we're talking about, so basically it helps when you get back into lab and you're in the room and then you can look at the machinery, but so there's like a plug in the wall, and then that plug, there is kind of like a box on the wall, and then there's the arm that comes out. So from a diagram and from my understanding, hopefully I'm telling you guys the right thing, all of this is happening in the wall. So it's not happening in the actual tube head. So these circuits are they're part of the electrical system.
And that happened before what we just studied about the.
Yeah, it happens before they're connected to it because it's like they have to communicate to it. So they have to communicate this decrease of voltage or increase of voltage. And there's some more pictures as we go through that kind of show it a little bit. But this is communicated to the cathode and the tungsten Phillip. But these coils, these primary and secondary coils, they happen before. So they happen before, Jenny.
What they do, why do they need to step it down?
So when you go to do your first step and create that electron cloud, they have to take that 110 volts that are coming out of the wall, and they have to reduce them down to 3 to 5 volts. So it's quite a step down. So if you get that picture, like you know that the volt coming out of the wall is 110, and that electron cloud, to get your initial cloud formation of electrons, you don't need 110, you just need 3 to 5. So it has to step down to reduce the energy to just give it all it really needs to create those electrons. And then the coils come into play on the actual specific how it does that is if there's more turns in the second coil, it's increased energy, increased voltage. If it's less turns in the second, it's stepped down.
So it's first stepping down with the less coils, and then it goes and heats up the filament and makes the electrons.
So
you need to step up to like shoot it across.
Yeah, so it steps it down to heat up the filament, and then it steps it back up to shoot it across. Exactly. That's it. I know. Go ahead. So I'll show you, I'm pretty sure they're both in the wall, and then there's wires that probably run through the arm. But what I know for sure is it happens before the electrons are able to even be produced or shoot across. This whole thing has to happen, and I'm pretty sure it's on the wall. But I'll show you a diagram that shows it, and it kind of confirms that. I don't think it's in the tube head because in the tube head we just have the vacuum, and then it has all the oil to insulate the heat. I don't think the transformers are in the tube head. Yeah.
Okay, this is like a weird question. I might even answer it when I ask it. But okay, so when you turn on the power in the beginning of the day, does that start making the electron cloud, or do you have is it when you push the button
No, it's when you flip on the switch. So at the beginning of the day, you flip on the switch to turn your unit on, and immediately you start to create an electron cloud. So they're totally ready and just sitting there bubbling off the tungsten filament. So the tungsten filament is where the electron cloud is. And they're just sitting there waiting, boiling off of it, waiting to go somewhere. And then when you push the button, you accelerate them and get them to where they need to be. Yes, you're welcome. So I think because, let's see, let me just look at the next slide here. I want to find a good place to give you guys a break, but I think I might have another. Okay, so this slide was showing, it's pointing to, this specifically is talking about the step down, and it's pointing to what the step down looks like. So see, there's more coils here, there's less coils here. So this red arrow is specifically pointing to what a step down looks like. This next slide, I can get over to it, is pointing to the step up. So there's fewer turns in the primary coil, more turns in the secondary coil. This side is controlled by kVp or kV, the kilovoltage. So when we're talking about the energy in the X-ray, we're talking about two things. We're talking about MA. You'll see it when you go in there. Remember, you guys had the scavenger hunt, and it's on the actual thing where you push the button to get the X-rays to come out. It says 65 kVp 7 MA or something like that. They all have it, and that's all you really have to. Those two things are what's creating this this energy. And so step down is controlled by MA. Step up is controlled by kilovoltage. There's more turns in the secondary coil than the primary. You can see that as depicted here. And it changes now the 110 volts to 65 to 100,000 volts, or 65 to 100 kilovolts. So it increases it hugely. That's a huge step up. And so that's depicted here in this one. So this is just showing, just to compare the step down, but this is specifically showing you the step up because there's more turns in the secondary coil than the first. Yeah.
The purpose of the step-up transformer is to shoot the electrons across.
To shoot the electrons across to the anode. Yeah.
You would say that step down is first and then step up is second.
Yes. Yeah. So step up happens first and step down happens first. My brain, sometimes I'm convinced I've said it right and I have say stuff completely backwards. And then students will be like, you mean this? And I never even heard myself say it. So never worry about correcting me because sometimes I flip stuff around all the time. But what happens first is the step down for the MA production of the electron cloud, push the button, step up to accelerate the electrons. Yeah, so it steps down to create the electron cloud, step up to increase the voltage to accelerate them over to the anode. There's going to be like a song that can be written about this or something.
Like another thing that we can compare it to, like
yeah, there's got to be some kind of a process that can be sharp. Yeah. Yeah, because the electron cloud, like when you turn on the machine, I think that's kind of always going because you always want electrons at your disposal. So I think that the step down is probably technically working more. Yeah, that's kind of my educated guess. Is that it's always, because you always want to have electrons at your disposal. So I think it's just always working.
So now we're creating the electron cloud. Step up is increasing the voltage to send the electrons over to the unit.
Mm-hmm. Yeah, you guys are getting it. It takes a while. Hala? Can you repeat what you just said? Yeah.
And then the other thing, just to make sure, so you said either a step up or down that forms the cloud. Does that mean that it is not forming in its tube?
So inside the vacuum, the electron cloud is constantly producing electrons. And so in my educated guess, I was going to say, I don't know what I was going to say. In my educated guess, I would say the step down transformer is always active because there's always an electron cloud. There's always electrons at your disposal. So I believe that the step down is probably always in effect. And then the step up just happens when you push the button to expose your X-ray.
Sorry, during the button push, is this when that happens and that movement happens like simultaneously?
So the thermionic emission is actually kind of the same thing as your electron cloud.
Okay.
That's a thermionic emission. So that happens over on the step down side, and the MA controls that.
It's just like a loop that's continuously going.
Yeah. You push the button, it increases voltage. You let go of the button and it kind of goes back down. And the auto transformer is keeping everything kind of copacetic, keeping everything from shorting out, letting it handle that big uptick of electricity. So that's what the auto transformer is doing.
So like there's just like wires, like you said, in the like arm, basically.
Yeah, I think there's just wires without getting, what we need is a tech, like one of those tech guys to come out and talk about it. Do we need an electrician? Well, Amy, when she taught this, her husband he's an engineer, but I feel like he might even be like an electrical engineer. I don't know. He's got some good knowledge. So she had that privy, she had that ability to go home and be like, honey, blah, 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 blah. I don't got that. My husband does do some electrical work, but not to that level. Okay. Let's see. So I want to get to a stopping point. I think there is a couple more slides, and then I'm going to give you guys a break here. Auto transformer gives the ability to alter kilovoltage of the X-ray machine. So let's see, I'll read my notes here. With transformers, it's important to understand the secondary coil determines the voltage. So on the transformer, whether you're talking about step up or step down, it's the secondary coil that determines it because it's either more or less turns. So the secondary coil determines the voltage. And then the correction for excess voltage happens in the auto transformer. That's why the lights don't dim and sparks don't fly. So that's the correction. It keeps it kind of all balanced. That's the auto transformer. Yeah.
So let's say we all are taking at the exact same time. Is there a chance to get like a light flicker?
I don't think so, because that's a great question, but I don't think so because I've worked in big offices where, had a couple, like I took X-rays at the same time as my neighbor, and I think they're all work independently. And then they probably, who knows, they probably wire in certain things. Maybe because they know medical offices and hospitals and, maybe they have more machinery. So they probably, make provisions for things like that. So I'm going to say no, but who knows? But I've never, we've had everybody, all 4 rooms going for years and nothing has happened. So I think each room kind of has its own safety, so it doesn't happen. Okay, so let's just look at the whole system here. So here we have, look, this is showing them inside. This is showing them inside the tube head. So, but see, hold on, I'm going to advance to the next one. Hold on. But see now here, but you're not going to get, let me put this to rest. You're not going to be tested on where the transformers live. Wherever the transformer lives, it can live happily. You just need to know what it's doing. You don't need to know where its home is. Now, you might be interested and want to know because you have a curious mind and you like to know things, but you're not going to be tested on where the transformer is actually housed. This does look like the transformer is inside the X-ray tube head, which, because I'm just not as smart as I want to be, I didn't figure that out. But it doesn't matter because there's no questions on the exam about where the transformer is. So feel better about that part anyways. So this is just a diagram showing that you have the low voltage or the step down. It's connected. You follow the little line. It's connected to the cathode. And then we have the high voltage or step up. It is connected to the anode. Now, this will maybe throw a little bit of a loop. In reality, the step up is actually connected to both sides because you need that voltage to accelerate them over to the anode. This isn't showing it. I think the next one does. That is sort of just a side note. I don't think there's any questions about that on an exam or a quiz, but it kind of looks like here it's exclusively one side and the other side, but the high voltage is actually connected to both. But the low voltage or step down, it's just easier to think of it that way as one on one side and one on the other. Connected to the cathode, the negative side, controlled by MA, milliamperage is MA, high voltage, step up, it's on the anode side, controlled by the kilovoltage.
That's basically what we need to know.
That's the big crux of it. That's really what you want to know, what controls it. You want to know why it's a step up, like the coils, the secondary coils. Those are some of the big take-home points that you want to know. What's happening, like, the step down creates the electron cloud. The step up is when you're accelerating the electrons. Those are the kinds of questions that you're going to need to know for quizzes and exams for this class, and then even for, down the road for like national board reviews. Here's another image again of this is the step down coil, because you see there's more coils on the primary, less on the secondary. Here's an image of the step up, fewer on the primary, more on the secondary, connected to the anode. And see, this image shows it. See how it's connected to this side as well. So the step up transformer has to be connected to both sides because it's accelerating them across. And then the step down only has to be connected to the cathode because it's only stepping down to create the electron cloud. So sometimes these images can look kind of confusing, but that's what this is showing, the step down with the difference of the coils going to the cathode, the step up with the difference of the coils, fewer and more going to the anode. Questions there? We're kind of hashing it over a lot because it's you just got to get it in your head. You just got to get the system down, think about it, write it down, draw pictures of it. And then it'll get in you'll get to the point where you are remembering all the different steps. Yeah.
Wait, so is it moving from this way over to the right side?
It's kind of weird because we think of things because we read, like from right or from left to right, like when we read. But this is showing it happening. Well, if you look at the screen, it's showing it happening from the right side of the screen. So it almost looks like it's happening in this direction. I think it's just a mental thing, but all you have to know is what's literally happening first is the step down and then the step up. Because first you have to have an electron cloud with electrons that are available, and then you accelerate them to the anode. So that's whether it's on the right or the left of the machine, or the picture, it kind of throws our mind off because we're used to thinking of things sort of in this kind of a sequence. At least I am, but
Maybe there's a YouTube video.
Surely there's a YouTube video. I'm sure there is. And actually, I wonder if I have one embedded in the slide here. Let's see. Here again is the entire system, but this time you see the control panel. So this is what's on the wall. It says 10 MA, 15 MA. Ours just says 7 MA. The on and off switch, it's plugged into the 110 volts, 36 impulses, within every time you push the button, it pulses 36 times. So there's just giving you a little bit more information. You don't need to memorize this slide or anything on it, other than just seeing that the wall mount that has like the exposure button tells you what the MA is, what the KVP is, and then you're going to have the wiring coming over through that arm, and then you have the tube head where apparently lives the transformers, which I didn't pay close enough attention to until now.
So
Now I'll never forget it. Okay, what?
I think the electricity is just constantly going on
Mhm.
each way, and like it just kind of like it turns on right there, and it's just like
Yeah, that's why I think you constantly have the step down being active, because you always need those electrons available. And then you'll excite it, you'll generate more when you need that high voltage to get those across. Okay, I think that's a good stopping point. Let me just click over at the next slide really fast and give you guys a 10-minute brain break. Yes, that's a good place to stop. So let's see, I'll have you 2:04, so 2:15. Come back at 2:15.
I didn't know I could check my, like, what I got wrong. Is there anything?
I might have found that one right.
I wish that I could say that it gets easier from here in this lecture, but it doesn't. I'm telling you though, guys, seriously, the next lecture is kind of challenging because it's I believe it's the next one anyways. It's more like biological changes, but it seriously gets easier after about that point. It gets to be much more like practical hands-on knowledge that you're actually going to feel like you're utilizing in lab. This is all like, oh, like, why do we need to know this? But it's, you know, it's important for us to know that we're dealing with a lot of energy and something that potentially, well, doesn't potentially, but almost always does some kind of cellular change because it's ionizing. So it's important for us to know it, but it's hard sometimes to just wrap our minds around it because it's just not really practical to taking X-rays. You don't think about it every single time, even though that's the hope, is that you will think about this process, I guess. I don't know. But so it does kind of, we're still kind of going along in this sciencey talk. So it is still a lot of things to wrap your mind around. So we're just going to keep barreling on through. Okay, so quality and quantity. So we're talking about quality of the actual X-ray beams and quantity. So we're talking, so it's like what kind of wavelengths and penetrating power, what's the quality of them, and then how many are there? So that's what we're talking about when we talk about the quality and the quantity. And the kilovoltage and the milliamperage, they determine different things. So we have the increase of the MA, because that's the part that's on the step down that controls the electron cloud, that controls the number of electrons that are available to us. Because that kicks in and starts to create that electron cloud, that is controlling the number of electrons available. So that is quantity. And it says why, but I just said why. Why? Yes.
On your slide, it says determines the number of photons in a beam, and you just said electrons. Is it technically both?
Okay, this can get confusing. Sorry, and I might sometimes misspeak. So once it's hit the anode, they have become photons. So once those electrons fly over, but at the filament, at the tungsten filament, we're talking about electrons still. So it's a little bit like, ugh. We're talking about electrons being created in that electron cloud. And if the more that you have, you're gonna have more X-ray photons. The minute they hit that, they're photons. So kilovolt peak, kVp, determines the energy of each photon. So this is affecting the quality of it. So it's kVp can also influence the quantity. And I know it says why, but I'm not, I mean, does anyone have like a random guess? I should at least give you a minute to just guess something. And some of you might know, I don't know, probably. I'm like, did you say you wanted it? No, you're just randomly thinking.
What did you ask?
Well, it says, the second one here says, there's a Y after it. So the kilovolt determines the energy of each photon, but it also affects the quantity and why. So Tala, do you think you got a guess?
I might be completely wrong, but maybe because you have, so the higher or the more kilovolts you have will affect the voltage quantity. So the number of these kilovolts will affect like the effect itself.
So when we think about what like when we push the button and it creates that high energy, like they fly over there, they're like the speed. The higher the kilovolt, the more that's going to happen. So the more that reaction happens, that not only helps with the energy of it, the power of what they're doing, but they're just going to fly over faster. So it's kind of like, you can think of it as just dialing up the speed, which dials up the strength of them, but also how fast they fly over. So then that affects the quantity. So the quantity the MA can only affect quantity, because that's how many available electrons you have. But kilovoltage can do quality and quantity because it's how fast it's happening. So the faster something happens, if it's just this constant reaction, you just automatically get more, right? Like if you and your neighbor are both eating jelly beans and it's like, you have 10 minutes and your neighbor eats them twice as fast as you, they've ingested twice as many jelly beans in the same amount of time. Does that make sense? Was that a good analogy, or did that just make like sense in my head and nobody else's?
So like the quality is like because of the different types of.
It's the speed, yeah, and the like literal like kind of energy or power. Let me see if I have a note that maybe describes it better. Increased kilovolt peak, shorter wavelengths, higher frequency, higher penetrating power. So when you increase kVp, you are going to effectually, you're going to create a better X-ray beam, because it's going to, you're going to create like a better image. It's going to, because those electromagnetic wavelengths are going to be shorter, higher frequency, closer together. And so they're going to penetrate better and create like a better image. Yeah.
Opportunity to lose energy if it's moving that fast.
I think
like a dispersion of energy.
Yeah, and so since you're dialing it up, it's just happening. It's happening. I mean, it is still pulsing. It's still, because it only happens on it's that alternating current. So it's still pulsing, but it's happening so fast, and it's just continually while you're pushing the button. So you're really not, that's a great question. It's maybe a little bit beyond my ability to give that like a super direct answer to that. But from what I know about the process, it's just in that window, you've turned the kilovoltage peak up. And so that you're going to have like higher frequency, stronger, more powerful X-ray in that time frame of that you're pushing the button. Well, we do talk about scatter and stuff in a minute, so maybe hold that. Maybe your question will be answered in a few slides. So more X-rays flying around is a general opportunity for more X-rays, more X-ray photons are flying around because of the increased KVP. So if you think of it, there's a thing in the book that says KL, this is an, I don't know if you call it I'm just going to say anagram, and I have no idea if that's the right word, but KLMN, I was going to write on the, I think the couple slides next will describe it better. It has to do with the frequency and the wavelength. And so let's see if this couple slides show it a little bit better. So KLMN basically will help you remember this because it's kilovoltage. Sorry if I wrote it all in a funny way. So kilovoltage, quality. So we got the K for kilovoltage, L for quality, MA, quantity. So that might help, just at least that piece kind of stick in your head. KL, and that's alphabetical, right? A, B, C, D, F, G, K, L, M, N, O, P, Q, R, S. So if you remember that little segment of the alphabet, KLMN, kilovoltage, quality, MA, quantity. Now, what's that? So this is just something for you to remember what controls what. So the KVP affects the quality predominantly. We also know, we already said that it does also control the quantity, but predominantly we're talking about, and that's kind of a byproduct of it, but the main thing is increased KVP is a better quality X-ray. And then MA, milliamperage, controls the quantity of X-ray photons. So that's what this KLMN is, just giving you a way to remember that KVP and quality go together and MA and quantity go together. Because there might be a question on the quiz that says the quality of a film is controlled by what? And then you have to know the answer is KVP, kilovoltage. It does. And so the question may say something to the effect of, I mean, it could either just say quality, or it could say something like, which one controls both quality and quantity, MA or kilovoltage. It would, but just as long as if you remember that MA can only affect quantity and nothing else, then you do pretty good. But that KLMN is kind of like a little thing to help you remember what goes with what. So the last couple things that will affect all of this is the distance. So the distance, and I'm trying to think if that's supposed to say in or is. If is a typo, I'm not sure. So the distance from where these X-rays are generated in the tube head to wherever you're trying to get to, that distance is also going to affect the image. So the further you are from the source of the beam spreads out like a flashlight. And so the number of photons are going to increase in the field of, they're going to fly out in a straight line, but they're going to fly out in a fan shape and they're going to disperse. And so this is something I feel like needs a picture drawn. But so the light that hits, think about holding a flashlight up to your neighbor's cheek. And if you hold the flashlight up to your neighbor's cheek from 2 inches away, you'll probably see perhaps like a circle of light. If you walk away and you hold the flashlight out here, you're going to illuminate their whole head. So think of the X-ray photons coming out of the source, flying off of the anode. and traveling down the BID, if that BID is that distance from the BID to the person is shorter, then you're going to have less of that dispersion. And if it's closer, you're going to have less of that dispersion. And if it's farther away, you're going to have more. So X-ray photons that spread out are not going to be useful to that small space that you want to cover the sensor. They're going to have hit the top of their head, or they're over here or whatever, because they've spread out and they're just not useful anymore to this small space that you need. So, and that decreases the intensity of the beam because you don't have as many. So that's affects quantity. You just don't have as many X-ray photons hitting the area that you want. Rate is exposure time. See, these 3 and 4 are like, why does it say is? Is that a typo? So rate and exposure time. So rate is exposure time. I think that's what it's trying to say. So when you push the button, it's called the exposure button, right? We say go push the exposure button. And how long? So how many of you heard the beep? And I said, hold it till the beeping stops in lab. When the beeping stopped, the whole experiment stopped. Experiment might not be the right word, but the whole process stopped. Like experiment, I don't know what the whole process stopped. So when you push the button and it's like beep and then stop, that beeping was the acceleration of the electrons flying over, hitting the anode and coming out the tube head. So the length of time that beeping lasts, it means more or less X-ray photons were produced. So exposure time also influences quantity, and that's just why. I never give an opportunity for anyone to answer the why. I always say it before, but does that make sense? That's why the quantity of the that's why the quantity of the electrons or the X-ray photons is affected by exposure, because if you press beep for like 30 seconds, like beep, and it just keeps going, then lots and lots and lots of X-ray photons come out. If you push it for half a second, then a lot less. So that's why quantity is a part of that exposure time.
Did you say that's how many, like, that's how long it's going to be like rolling the electron at the other side, and the like KV that like shoots it out, like all that's going on at the same time?
Yeah. So as you push the button, that whole process is happening, and the X-ray photons are flying out of the BID, coming to the sensor, the whole time that button is being pushed, and you hear that beeping noise.
Basically, the amount of X-rays that are being exposed.
I think it's just like an audible trigger that the process is happening. Radiation is occurring. So if you push the button and you don't push it hard enough and it errors, maybe nothing happened. Maybe no X-rays were ever produced. Everyone will do that. They won't push it, or they pushed it and let go too soon and it errors. And that's just either maybe it started, but it didn't finish, and so it errors, and then you just have to kind of reset it and press it again.
Will it ever just like kind of halfway do like an X-ray? Can you like accidentally like do a crappy one?
It doesn't seem to ever come up on the, I don't think so, because when it errors, nothing ever comes up on the computer. So I think when it does it just doesn't finish the process, and then it just doesn't come up, because I've never seen a picture come up before when it has errored. Okay. Now this can be a good test question. So we'll make sure that you guys understand this piece here. The relationship between exposure time, pushing the button, how long you've exposed the patient to radiation, and MA, they are inversely related. So both have a direct effect on the number of X-ray photons being produced in the beam. So how long you push the button and the beeping sound goes, or how high your MA is and how many electrons are available. So MA, so let's see, we'll go down here. So milliamperage requires the amount of MA or milliamperage required for any given exposure time is inversely proportional to the exposure time. So if all you really need to know, and you guys can't control MA, so this is all just in theory. You can control exposure time though, because that's, you know how you select, so far you've all just selected bite wings. On the little picture on your thing, it says anterior teeth, premolars, maxillary molars, mandibular molars, bite wings. Those are like generally the main things. When you are choosing different ones, that's your exposure time. It's changing it ever so slightly, ever so slightly. So it doesn't make a huge, big difference if you push the wrong button and then you take an X-ray. Sometimes it matters more than others. But anyways, I get off the topic. So the higher milliamperage, the less exposure time you need. But you can't change the milliamperage on our machine, so don't stress about it. But you do need to understand that if it was an old time machine and you could change MA from like 5 to 7 to 10, you would have to then change your exposure time. If you're going to raise one, you have to lower the other. If you're going to, opposite. If you're going to raise milliamperage, you need to reduce exposure time. If you're going to increase exposure time, you need to reduce milliamperage. They teeter-totter.
And also, if you let it there for a while, like close it, and that's when you get the tissue damage. Right?
Yeah, like you just want to send enough high quality X-ray photons to get your picture. We want the minimum amount to get a good shot. And pretty much that's what happens in there. It's all kind of been dialed in for you. There was a time probably 30 years ago when you had to like figure it all out and make sure you had everything set just so, but now it's all pretty much, set there for you. Okay, this is going to give everybody a big headache. Anybody here love math? Oh, so you guys may actually have to teach me this. I'm going to tell you this right now. There is not going to be a problem on a quiz or exam where you need to do this, this actual problem, the actual calculations. Yes, I agree, Brandon. I am not going to make you actually do a calculation. There's a concept here that you need to know, and there will be a test question on this concept, but I love science and I love biology and microbiology, all that kind of stuff, but math and me get very confused with each other. So I don't even pretend to really want to walk you through this. So I'm not going to make you do it on an exam. I don't think there's going to be any actual calculating on the boards. An inverse square law question, highly likely, but an actual calculation, I am feeling like the answer is probably a hard no. I'll ask Amy but I don't think Amy, when all the 10 years that she taught it, I don't think she ever made anyone do a calculation either. So that tells me it's probably not likely that it's a board question. The concept though, you do have to kind of understand the concept. And I still go back to the flashlight. So an X-ray travels from the point of origin, popping off of that anode, and then they diverge like a wave of light and spread out and cover a large surface. So just like we said, it's like a flashlight. So they disperse. The inverse square law says the intensity of the radiation is inversely proportional to the distance that travels. So if the distance, so let's think of the BID. So if a BID is real short, then the X-ray beam is more intense. If the BID is longer, your X-ray beam is going to be weaker. So then you'd have to increase the intensity, the power to make up for that length of distance. And there's a specific formula that you could do to figure it out. So basically, like here in this image, if you double the distance, if your BID goes from 8 inches to 16 inches, the power or intensity of your beam reduces down to 1/4 of the intensity. So that's why they call it an inverse square. So the intensity decreases as the length of your BID increases. So the longer of a BID you have, the weaker of a beam you have. And so you'd have to increase, your power or intent. Let's see, what would you do? Do they want you to increase MA or KVP? Let me see. Maybe the next slide says it. We again don't change the length of our BIDs. So it's really not like something you have to know for taking pictures in our clinic, because we only have one length. But this is definitely a question that is the concept of it. So you can see here over here in this other diagram how so we have the intensity of the image, this number 1, and as the BID, let's pretend that this movement of it going out is a length of a BID. As we go to a longer BID, those same amount of X-ray photons, say there's 4 of them, let's just say there's only 4 electron photons, they'll now hit this space. So they only have 1 here, 1 there, 1 here, and 1 here. So the intensity, you have a bigger surface area and only 4 little old electron photons to hit this big surface area, because it keeps broadening. It keeps coming out like a big fan. So it's going to be a bigger surface area, and just the same amount of X-ray photons. So then if you go even farther than that, it's not doubled, but it's like because it's inversely. So this is where the math, it's 3 times as weak and then 4 times as weak. So it goes a 4th, a 9th, and a 16th, and that's where the math specifically comes in. And that's why I'm not going to do any of these equations, because my brain doesn't like it. But I just think about it in sort of a visual, like I think about it in a picture. Think about it's simply the farther it has to go, the more the beam spreads out, but you don't get more particles, more X-ray photons, they just spread out. And then you're trying to hit a bigger and bigger space with that same amount of X-ray photons. Does that make sense? Oh, good, because this is like this is the part I hate most of all of talking about this. Now the slides, there is a couple slides here that has, it's your turn. This is for any of you who do math, do this and maybe you'll come up with it. And if you want to share, you don't have to do it now, but the question is, a quality dental radiograph is obtained using an 8-inch BID and an exposure time of 3 impulses. See, this throws me. The 8-inch BID is removed, double the length. A 16-inch BID is now used. What should the new exposure time be to maintain the image density? So we need to increase. Bottom line is we need to increase the amount of X-ray photons that are coming out. That's basically what it's saying. And then it gives you this formula. So you can say precisely, oh, I need to increase it to this many impulses. So it's a mathematical formula that is basically based on this here. This is the formula. So it's original MA times your exposure time, your new equals or over your new MA times exposure time. Or maybe that's, I don't even know, you guys. I really don't. When it comes to this, I'm just like, what? You don't need to know it for a test. And I am 99.9% sure a board is not going to have you do math, because they just ask you multiple choice questions. So oh, you know what? probably just basic algebra, and my brain hated that. I mean, I got through it, but that was years ago. So if you want to look, oh,
Sorry.
what?
I just clicked on your thing.
Yes, it's a good visual. Although his voice is kind of weird, but. So here is this, so there's the, you know, like if MA is, or the exposure is set to 1, and you go from an 8-inch to a 16-inch, and then they do whatever their math is, and then this is the equation, and it ends up X equals 1/4. I'm not a math teacher. I never claimed to be, and I don't like it. But what I do know is it becomes less intense. And if you want a nice kind of visual example of it, go to this last slide. Oh, sorry. So the answer, since the beam will be 1/4 as intense, it's reduced its intensity by 1/4, you'll need to increase the impulses. You have to basically increase your exposure time from 3 to 12 impulses. How many impulses did we say were in 1 second? Do you guys remember that? 60. So 60 impulses in a second. So basically you just have to increase your exposure time if you have a longer tube. I won't click on here just because it might kind of mess up I don't know which screen it'll pop on, mine or this one. But this is a video that just shows he's got like toast, buttered toast, and he's increasing the distance, and he's showing how the butter is really, really thick on the 1 piece of toast, but the minute you double the distance, you get 4 pieces of toast with the exact same amount of butter as the initial one. So now the butter's thinner on those 4 pieces of toast. And then if you go even double that again, then you have 9 pieces of toast with the exact same total quantity of butter that was on the original, just spread even thinner still. So it's a kind of a visual. It still doesn't help you with a math equation. It's more like, you know, you can know it one way, but you don't have to do a math equation, so don't worry about it. But I don't want you guys to feel like I'm just dropping the ball on this. If anybody feels like they're worried about an assessment or they're worried about the national board, come and talk to me, and I'll also talk to Amy about where she took it and how, you know, if she said something more to get you guys prepared. But I honestly think they're not going to have you do calculations on the national board. I really don't think so. I never did, and I took the national board. Okay, so we got to do, oh my gosh, it's 5 minutes. I'm not going to get through all these slides. Okay. So what is the best quality and quantity X-ray beam to expose a patient to? You want to expose a patient to a high frequency, short wavelengths, high frequency, high energy, and they're going to penetrate better. So it's a higher quality power of an X-ray beam than something that comes out and it kind of has like some weak ones that kind of go through like the cheek, but then they never get to the tooth, they never get to the sensor. So all they really do is cause some biologic, you know, damage, and then they're done. And it's like, well, we don't need those kind. We want the kind that are going to get to where we want them to be. So here it's showing, this is like a cross section. Let's say this is a cheek, and these are all the atoms inside of a cheek. And we are showing how a longer wavelength, so the wavelength from crest to crest is longer, lower frequency, because if we count up the peaks from here to here, there's fewer. So this is low frequency, long wavelengths. They come along and they get kind of absorbed in the cheek. And then we come down to a medium one. The KVP has increased, the power has increased, and it's like a little bit tighter, a little bit faster, and it gets farther through the cheek, but still gets absorbed in the cheek. And then a deep penetrating, the KVP is where it should be. We have the optimal amount of power, and it's creating nice, tight, short wavelengths, high frequency, good penetrating, goes all the way through the cheek. to the teeth, and then to the sensor potentially. So in order to get these, so you can see on this side of the deep penetrating, we have high KVP, high frequency, short wavelengths, high energy, complete penetration. On the short penetration side, we have low KVP, power's turned down. You can think of KVP as just power, it's turned down. Low KVP, low frequency, low wavelengths, low energy. So we're just not going to get through to where we want to be. There's just, okay. So what I'm going to do, I have to stop there and I have to talk through the rest of it. I can't just leave it for you guys to finish the PowerPoint on your own time. So we're just going to have to pick up where we left off on next Thursday. Go through the PowerPoint, if you want, but I want to do this because this is like the heaviest stuff. And so I want to be able to answer your questions live, but I'm not going to hold you over and we're basically done. So I'm going to stop the recording and I'm going to post what we have so far.